This is now a problem in chapter 11 for a bowling ball rolling up this ramp. Here, you can see it a little better. And so the setup is like this. We have a ball that's heading up the ramp. The ramp is a height of 0.5 meters. And we're going to need to calculate how fast it's going at the top of its height, which means we want to find V final at the top, okay? And this initial speed, the initial velocity of the center of mass is that it is 3 meters per second. So that's of the center of mass. That's really, you can think of it as the speed that it had there, also before it got to the ramp. And so this is set up very nicely for energy conservation. So we're going to look at that. So we'll call this we want energy initial, energy final, and we'll set this as our y equals 0. And so energy initial, the initial potential energy is 0. The final potential energy is mgh, where our h is 0.5 meters. Our initial kinetic energy is 1/2 mv of the center of mass, this v initial squared, plus, we've got the rotational piece, plus 1/2 I omega squared, because the ball is both not sliding, but it's translating, it's moving up the incline and rotating. So we've got both of those pieces. And the same thing happens in the final situation. If we've got a final speed, that's 1/2 mv final squared plus 1/2 I omega final speed, right? If it's going slower or faster, then it's going to have a different omega. And so we say these energies are equal to each other. So I just get 1/2 mv initial squared plus 1/2 I omega initial squared is equal to mgh plus 1/2 mv final squared plus 1/2 I omega final squared. And it looks like I don't quite have enough information here because I don't have the mass, I don't have my moment of inertia, I need to connect my omega to V, so that's not so bad. I can say my omega initial is equal to V initial over R, and then I can do the same thing over here, so I can make that substitution. The other substitution I can do is say this is a ball, so we can treat this as a sphere and say the moment of inertia is equal to 2/5 mr squared, right? So that would be my moment of inertia. So if I put that in to right here, that's going to help me out a little bit. So I'm going to rewrite this to say I've got 1/2 mv initial squared plus 1/2 2/5 mr squared v initial squared over r squared, because I've substituted in my omega, is equal to mgh plus 1/2 mv final squared plus 1/2 times 2/5 mr squared times v final squared over r squared. And what this does immediately, if we look at this, is we can recognize that our r squares are going to cancel, which is nice. And then I look and I've got a mass in every term. So I can divide the entire equation by m. So we'll get rid of the m's everywhere. And this really cleans things up. Notice I've got a 1/2 v initial squared and a 2/10 v initial squared. So I've got 1/2, which is 5/10, plus 2/10 v initial squared. So that 1/2 comes from there, and the 2/10 comes from there, is equal to g times h plus, same thing over here, 5/10 plus 2/10. So I didn't cancel out the 2's in the 1/2 and 2/5 because I need a common denominator to add this to the 1/2 v final squared. Okay, so this gives me 7/10 v initial squared is equal to g times h plus 7/10 7/10 v final squared. Now I can finally put some numbers in. So we go back up here. Our initial v is 3 meters per second. Our height is 0.5 meters. So g times h is going to be 9.8 times 0.5 meters. So I'm going to get 4.9 meters per second squared, then times the h is another meter, plus 7/10 v final squared, and then v initial was 3, so 3 squared is 9, so I get 63/10 meters squared per second squared. So this is a 6.3, obviously. So 6.3 minus 4.9 gives us, I think, a 1.4 meters squared per second squared is equal to 7/10 v final squared. We multiply both sides by 10/7, right? 10/7, 10/7. That gives me 14/7, or 2 meters per second squared is equal to v final squared, or my v final equals the square root of 2, which will be 1.4 meters per second. So that's the final speed at the top of the ramp. So right up here, that's my final speed. Now part B says if the ramp is 1 meter high, does it make it to the top? So we can look back at sort of our main equation, which is right here. So I'm going to pull this out for part B to say I've got 7/10 v initial squared equals gh plus 7/10 v final squared. Here we're saying if h is equal to 1 meter, so this gives me 9.8 meters per second squared plus 7/10 v final squared. I have the same initial that I had here, so that would be in this, so I would get 6.3, meters squared per second squared. And notice now I would have, if I bring the 9.8 over, I would have negative, and I can't have v squared being equal to a negative number. So in fact, it does not make it up the ramp. And so that's the answer to part B. So in part A, we can find a final speed. If the ramp goes up to 1 meter high, the bowling ball does not make it up the ramp.